Hi everyone, welcome to Tech Thursdays. For those who may not know, Tech Thursdays are events for knowledge sharing, inspiration, and to connect with tech professionals and enthusiasts alike. We kicked off our first ever Tech Thursday event in Feb this year, a dev night featuring Yuval Lowy. This time round, we're going virtual with a Derivco webinar on Kafka. To keep you in the loop, here's the agenda for today. First up is our CEO, Kiresh Bihari, who will deliver the welcome address. We will then start the webinar presented by Niels Berglund and Charl Lamprecht that will run for about an hour, followed by a 30-minute Q&A session. We will then end with me closing the event. Just a few things to note. We want to keep things quite interactive, so feel free to ask questions during the webinar and of course at the end in the Q&A session. Questions can't be asked verbally, so simply type them in the question bar. Just look for the question mark and speech bubble icon to the right of your screen. Niels or Charl will answer when they get a chance. Now, we can't promise that every single question will be answered, so if you see a question that you like, hit the thumbs up button and we will try to get to the most popular ones first. And finally, there is a 15 to 30 second delay, so please keep that in mind. I think that covers everything. We hope you enjoyed today's session. Feel free to tweet, comment, and share on social using the hashtag Derivco Tech Thursday. We are active on Facebook, Instagram, Twitter, and LinkedIn. But enough from me. I now hand you over to Q, who will officially open the event.
Hi, everybody. Welcome to the first ever Derivco webinar. And thanks to all our local in South Africa and international visitors that have decided to join us for this. I think it's important just to point out that, obviously we're having a webinar for the first time ever, mainly because of the uncertain pandemic-induced times that we find ourselves in, but also really appreciate that everybody's made the effort to contribute towards flattening the curve. We also thought it was important that during this time we spend a lot more efforts on trying to increase our knowledge and learn new things. I think the pandemic itself has forced us to challenge the way we think normally about the way life is lived, and what better chance do we have now than to take advantage of that to connect around the world and learn something new from a couple of experts that I'm about to introduce. I think today's talk is mainly centered around Kafka, and it's really important because Kafka is exploding as a technology across the world at the moment. A third of all the Fortune 500 companies utilize Kafka to take advantage of live data streaming, abilities to interact better with their customers, to create new business opportunities for them. The likes of LinkedIn, Microsoft, and Netflix are utilizing it in any number of ways. They process over 1 trillion messages just from those companies alone on a daily basis. At Derivco, however, technology is at our core, and we like to keep on the front foot with pretty much any new technology that's going to help us get stronger and better at what we do. We use it predominantly for event streaming, and it's forcing us to, again, be a lot more aggressive in our analysis and our response to dealing with real-time events. Now, I'm lucky enough to work with some of the best people in the technology industry in the world, and that includes the likes of people like Niels and Charl, who you guys are about to hear from. Niels, a software architect at Derivco and a Microsoft Data Platform MVP, who loves databases in general. I would like to say more than his wife, but that's not true. He loves his wife tremendously, but he's pretty knowledgeable on databases. He's also shown a keen interest in message-based applications and distributed and content systems, and recently has dug into the world of data science with some of the newest Microsoft R technologies. Charl, on the other hand, a senior developer at Derivco again, and a self-proclaimed real-time data dude. And I don't know if that name does him any favors, but you guys can be the judge of that. He loves working with data and integrating systems, and he's done so for 13 plus years. He digs Apache Kafka and is one of the first Confluent certified developers for Apache Kafka in South Africa. I think it's time that you guys hear from the experts rather than listening to me talk. So over to Charl and to Niels for Conquer Your Data with Kafka and ksqlDB DB.
Thank you, Q. Quite a glowing intro. No pressure after that, eh? So, hi everyone. Hi again. I'm Niels Berglund, and with me today I have Charl Lamprecht, Charl is actually the smart one. I'm not even the pretty one, but so we are here today to talk about Kafka and ksql DB and conquer your data with Kafka and ksql DB. Before we drill into what Kafka and ksql DB is, let's talk a little bit about in the title here, conquer your data with Kafka and ksql DB. The operative word here is not Kafka or ksql DB. Well, I love ksql DB because it has DB in the name, and then as Q said, I'm an old, old in many ways, old database developer. So DB, anything with a name with DB in the name is awesome for me. But no, it's neither Kafka nor ksql DB, but it is data. So let's talk about data, and I have some quotes here on this slide that you will see in a second from a book by a guy called Brad Smith. He's lead counselor in Microsoft, worked together with Bill Gates for many years, and he wrote this book about essentially data and Microsoft's way to Azure and the cloud and stuff like that. And what some of the quotes here is that civilization has always run on data. So data is the important bit. Moses came down from the cloud almost with his tablets, right? From there on, we have the engravings from cavemen. We have the Egyptian pyramids with pictures, which is data, right? And today everything runs on data. So Q and his leadership team is mouse over Excel spreadsheets and stuff to see where the business is going. Data is the important part. And some people says that data is the new oil. I do not agree with that at all, because oil is a scarce resource. Data, on the other hand, we are producing more and more data as we go along. And even when economies slow down, we are not slowing down the production of data. Now we're sitting in a lockdown here in South Africa. I don't know where you guys that are abroad, if you're in a lockdown or not, but I can guarantee you that there is no slowdown in production of data, right? I have some more. I have a couple of research numbers that from its IDC that did research together with Seagate about how much data we have in the world. So 2018, the IDC research came up with that we have 33 zettabytes of data worldwide. Okay, so in my home PC, I have hard drives which gives me 6 terabyte worth of data, and that to me is a lot. 1 zettabyte is a billion terabytes. So 33 zettabytes, it's a shed load of data. But that's not enough. They are thinking that by 2025 we will have 175 zettabytes of data. 175 zettabytes. And the thing is here, why I'm bringing this up is that we need to be able to handle this data. This data can give us insights, and we need the tools to be able to evaluate, get insights in the data. And that's now where Kafka and ksql DB comes into play. And also, Q mentioned in his intro here that at Derivco we are doing real-time stream processing, and it is extremely important that we are doing real-time, look at our data in real time to see where we're going, to see what is happening, because if we are not doing it, we will be left behind, and soon our company will not be anymore. Right. So that's a little bit about data. Now, back to the normal program. So the agenda for today is that we will start with a quick overview of Kafka 101. You guys that know about Kafka, you may be bored. For you that haven't heard about Kafka or don't know that well, it may give you some extra information what it is. We'll then go over and look at CaseEqual DB and what that is. And finally, Charl will do some really cool real-world examples, how we can get insight in our data by joining Kafka together with CaseEqual DB. In between here as well, between the Kafka 101 and CaseEqual DB, Charl will do some simple samples to just show you what this is all about. Cool. So Kafka 101, we'll talk here a little bit about the history behind Kafka and then what it is. So Kafka started back in, well, around 2010 at LinkedIn, where they wanted to replace their existing messaging system. So 3 or 4 guys at LinkedIn got together and started writing this thing that became Kafka. They open sourced Kafka in 2011, and in 2014, these guys that developed Kafka at LinkedIn, they moved over and founded Confluent, which is the commercial arm of Kafka. And Confluent gives you support, training, etc., etc. At Derivco, we have a support contract with Confluent, and it's awesome. We can call them anytime, day or night, and get help if we run into problems. So that's a little bit about the history behind Kafka. So Kafka is when you read the docs around Kafka, when you read what Kafka is, it says that it is a distributed streaming platform. Right? And this distributed streaming platform has 3 characteristics. You are publishing and consuming streams of records. Well, you can exchange the records for messages, events, call it whatever you want, but you publish and consume. And you can, in addition to publish and consuming, you can also process these streams in real time. And that is what kind of differs to an extent between Kafka and other message queuing systems. So Kafka as such is not a message queue system, even though you can actually use it as such. The third thing that Kafka is doing, it is by default, we are persisting these records onto disk. And which gives us then, we'll talk about that a little bit later, but it gives us the ability to replay messages to consumers, to go back in time and find a message, etc., etc. So I said that there was a difference between Kafka and message queue systems. And one of the big differences here is that Kafka is not a queue as such. It is a commit log. So essentially, these messages that we are publishing, they end up in a log file. Well, actually, they end up on multiple log files, but more about that later. And why is a log a good thing? Well, you guys from Derivco that has worked with me in the past, you know that years ago, when guys came and said to me that, hey, this thing that you wrote, it's not working, it has errors, what do we do to fix it? The first thing I said was, what does the log file say? Because we are trusting the logs, they are trustworthy. We expect to find things in log files. And that is how Kafka is working. And these logs, they are distributed, so we can scale out. So coming back to LinkedIn, in 2016, I think it was, they daily drove 1.4 billion messages through their Kafka infrastructure. And they had around 1,500, actually, I think it was 1,400 brokers. So to scale out is important, and these distributed logs gives us the ability for that, and also resilience. So if we have a cluster of brokers, we can lose some brokers in that cluster without losing any messages, because the messages are distributed throughout these brokers. The logs are distributed throughout these brokers. So I mentioned before that there is a difference between Kafka and message queuing systems. So let's have a look at that. So here on the left-hand side, you see a typical message queue system. You have a producer to the left here, and the producer publishes in messages into a queue. That's the light blue thing here, right? And we're seeing how we have 4 messages there, message 1, 2, 3, and 4. We have also 2 consumers, consumer 1 and consumer 2. They are both reading from the same queue, and they are reading off messages from the queue. And when I say they read off messages from the queue, I'm saying that when consumer 1 here reads message 1, that message is now gone from the queue. When consumer 2 reads message 2, that message, that event, that record is now gone from the queue. If I would want consumer 1 and consumer 2 to get the same messages, so that consumer 1 would get message 1, message 2, and consumer 2 would get message 1 and message 2, we would need to spin up another queue. And consumer 1 would read against the first one, consumer 2 would read against the second one. And sure, that's not a problem, but, well, the problem is really that we are now duplicating. We are now having twice the amount of data, and that can be a problem. Cool. Kafka, on the other hand, so this blue thing here is no longer a queue, but it is a log, and messages is being published into the log. And the consumers are reading based upon an offset in the log. And we'll talk more about offsets in a couple of slides time. But the first message, that will end up at offset 0, message 2, offset 1, etc., etc., etc. And now here in the Kafka world, we have 3 consumers, consumer 1, 2, and 3. And consumer 1 has been connected to this log for a little while, and he now reads off message 4, which sits at offset 3 over here. Consumer 2 came in a little bit later, and he has now reached message 2. This message has already been read by consumer 1, so we do not need duplicate logs here. We're having one log for this particular topic and partition. We'll talk about partition in a bit. Consumer 3, finally, he has just starting up, and he reads from the start of the log from offset 0. All right, so that's a little bit of a difference between Kafka and message queues. Some key concepts here in Kafka. We're talking about clusters and brokers, and well, you guys and girls out there, you are IT people, you are PC savvy, you know what a cluster and a broker is. So broker is essentially a node, a server, and even if you have Kafka on one broker and one broker only, we still see it. Kafka still treats it as a cluster. Right. Then we're talking about topics, partitions, offset, and consumer groups. And let's go and have a look at topics and partitions. So, as I said, I'm a DB guy, and I'm trying to refer everything back to a database. And a topic is essentially a table in a database. And this table, this topic holds records, events, streams of messages that are kind of like-minded. So in Derivco, we are looking at wagers. We are talking about logins. In a retail scenario, online business, we may talk about orders, etc., etc. And these now messages that comes into the topic, they have a schema of some sort. And Kafka supports JSON. It supports Abro, CSV, and recently we now have also support for protocol buffers, protobuf. The message that we pass into the topic has essentially three parts, 3 properties. It has a key. I'll talk about that in a bit. It has a value. The value is actually the message, and then Kafka assigns a timestamp to the message. when we create a topic, we give it properties. So we have a retention period. Don't forget, a little bit ago I said that we are persisting messages. So the retention period defines how long should we keep a message in the topic. We can set a compression type in order to compress the messages sitting in the topic, how many partitions we are having, and also a replication factor. And the replication factor essentially says how many copies of this topic will we have. And on the right hand side, we see a picture. We have a 3-broker cluster, broker 1, 2, and 3, and we have 2 topics, T1 and T2, that are sitting across these 3 brokers. Right? A partition. So when we are, I said above that when we're creating a partition, when we're creating a topic, when we're creating a topic, we are defining partitions, and partitions is actually where the data, where our messages will be stored. The partition is the log. The partition is the actual log, and by having a partition, we get scalability and we get ordering, which is extremely important. And me as a publisher, I am controlling the partitioning. I'm controlling where to send this particular message, and that is based upon the key in my message. And to the right, we see now another picture here where we're still having broker 1, broker 2, broker 3, and 2 topics, T1 and T2. And both of these topics have 2 partitions, P1, P2, P1, P2. Then these purple, this garish color here, Charl wrote this picture, drew this picture, so I blame him for the colors. The purple things here are the replicas. So here we're now having a, when we created these 2 topics, we said we should have a replication factor of 2. And if you see here, this little F, T1F and T2F, that means that this topic is actually the follower. In Kafka, we're talking about leaders and we're talking about followers. And Charl will talk about that in a little bit. Cool. That was topics and partitions. Offsets them. So I've already mentioned offsets. And so when we are publishing in now a message to a partition, it ends up in the log and is being assigned a sequential ID, and that is the offset in the file. So the offsets are obviously unique within the partition, and me as a consumer, I'm indicating where I want to read from. So I can start to read. So when consumer 1 logs in here, connects in, he can say that I want to start, I don't want to start from beginning, but I want to start from maybe here message 3, which is offset 0, 1, which is offset 2, etc., etc. Right. And the offset and the partition gives me now a way to replay data. So let's say that consumer 1 has read a message 1, 2, 3, and 4, but then he realizes that, ooh, crap, I have messed up here. I've lost message 1, 2, and 3, or I have lost message 2 and 3. He can then say that, okay, let me start reading from offset X, and he will get all those messages again. Final thing before we go over to some demo code is consumer groups. And so we have consumers. And so consumer 1, consumer 2, consumer 3. One thing here, in order to guarantee order, is we're saying that you can only have 1 reader against a partition in a topic. Right? So there is only 1 reader that can read from partition 1 in topic A. But if we're looking here at topic B, partition 0, we're seeing we have 2 readers. We have consumer 2 and consumer 5. Why this works is because we can only have one reader from a particular consumer group. So when we set up a consumer, and Charl will show how that is done in a sec, when we set up a consumer, we are saying what consumer group he or she belongs to. And then Kafka takes care of the fact that we can only have one consumer from one consumer group against one partition in one topic. But I can easily read from multiple partitions in one topic, or from, well, I can easily read from multiple topics as well. In this case, this consumer group A, the top one, is interested in both topic A and topic B, whereas consumer group B is only interested in topic B. And since we already have a consumer reading from partition 0, this consumer 4 will now sit idle and not do anything. So that was a whirlwind tour about topics, partitions, consumer groups, and offsets. And now hand over to Charl to show us some code around this. Take her away, Charl.
Awesome. Thanks so much, Niels. That is a very cool introduction into Kafka. So there's one question from Wesley Robb, which I'll address just now. This is the first technical session today, and what we aim with this first session is just to show very quickly how easy it is to spin up a production-grade producer as well as a production-grade consumer, so that you can actually start working with your data in Kafka. And after that, we'll jump into some cooler demos. So a question from Wesley Robb says, how does the consumer know which partition to look at for a given topic? Excuse me. So when you spin up a consumer group, you can have multiple clients consuming from that group, and there will be a leader for that consumer or a controller for that consumer group. And that will evenly distribute all of the partitions that need to be consumed within your consumer group. And that's in effect how the consumers will know which partitions they need to serve. So they're basically chatting to a broker, which is the controller, and that broker will send them meta information that says, you've been assigned these partitions, and they'll basically go to those brokers and say, give me the next set, give me the next set. So let's jump into this. Now, before we get started with our first producer, just quickly how to get started with your first Kafka cluster. There's various options. Let me just get that off screen. So the first, or the best place to probably start is to go to Confluent.io download. And there you can either sign up for the managed service, which is free of charge for 3 months, or you can download some of the packages from the self-managed packages. Now, this includes Ansible playbooks. It also has Docker images, which we will be using locally today. There's also Kubernetes operators, and they've got the tables if you want to basically run it locally. So with that, we'll get started. We've got a local cluster set up, and let's go and write a producer. So we're going to get started with in our PowerShell over here, and we're going to be creating a .NET new console producer. I've already spun this up just for time saving. And then we need to add 2 packages. The first one is the Confluent Kafka package, and this will allow us to actually create a producer, a consumer, or even an admin client. And then we'll also add the Newtonsoft.json package because we want to work with some JSON. So we'll open up this in code. I'm using Visual Studio Code here. You can obviously use any editor that fits your style. And we'll go right into our program, and you'll see that this is just a normal .NET C# application. We'll get started by bringing in the packages we want to use. So we're going to bring in Confluent, Kafka, and we'll also bring in Newtonsoft.json, and more specifically, the link library over there. Okay, so this is a normal Hello World application. We'll have 3 parts to our application over here to get started. First, we'll define our configuration settings. Then we'll create our producer. And lastly, we'll send some messages. And just to close down, we'll actually just flush and wait for some statistics. Now, any client that you work with Kafka, you start off by specifying some configuration variables. So we'll create a new variable config. That'll be of type producer configuration. And now we can tell our client all it needs to know about the cluster. So the first thing that our client needs to know is the Bootstrap service. And Bootstrap service is in effect just telling our client, where can I go and find a Kafka broker? Now this is a comma separated list, and the more you specify, or the more nodes you specify, the better. Because if you happen to have a node that's going through a rolling restart, and you've got 2 or more Bootstrap service specified over here, the client will actually handle this. And any node in a Kafka cluster that's active can give you back all of the meta information you require to your client. So we've got a cluster running at localhost on the default port 1992. Then we also want to give our client a client ID, and client ID is a very powerful field to use in debugging and in if you're doing fault finding, and we'll just call our client ID producer 1, and it's good to have this unique across all of your instances. Then we'll go and say we want, we'll go and specify the ACKs we want. Now ACKs is saying what kind of acknowledgement or guarantees do I want that my message is safe. So we'll go and specify that we want ACKs.all because we want to know that our leader has the message first of all, but also that all in-sync replicas that's specified has this. So in-sync replicas is basically brokers that need to serve this topic as well, and as long as they are up and happy, they'll have an in-sync replica set of the messages as well. The next setting we'll do is our partitioner, and partitioner is saying how do we want to actually distribute this across our partitions. The default is to use a key-based partitioning function, which comes out of the box, and that will normally do a hash function and do a modulus across the number of partitions in your topic. We will go and set this to partitioner.murmur to random. And the reason we're using that one is that that's the default in CaseEqual DB, as well as in Java clients. And if you keep these the same, it means that you don't need to go and repartition your data if you want to do joins later on. Now, the next 3 settings has to do with controlling a set of messages being sent. So Kafka does send messages in many batches or sets, and we can go and control this. And the reason it does this is actually to save on bandwidth and network chattiness. So the first thing we can do there, and Niels mentioned this, is the compression type. We are going to set that to LZ4. You've got all of the main ones there, Snappy, gzip, ZST. All of these has pros and cons, so go and read up on it if you don't know which one to use. And then we'll set another setting to do with our sets, and that's linear milliseconds. And linear milliseconds tells the client how long to wait around for before actually sending off the batch. And this is in effect the latency that you're willing to wait for before sending off your set. And one setting that works in conjunction with that is batch num messages. And this is saying how many messages does it need to wait for. And whichever is first from linear milliseconds or batch num messages, you'll see a set being sent. It's important to know that a set is basically sent to a partition. So every partition you're publishing to will have one of these sets building up. Another setting we'll just want to quickly throw in here is enable idempotence. And enable idempotence is pretty new. We'll set that to true. And that's giving us a guarantee that we'll in effect have, after some time, a single message on the other side of the wire. This is setting some properties intrinsically, including the maximum number of in-flight messages, retries, and so forth. Lastly, we'll set statistics interval milliseconds, and we'll set that to 10,000, which is basically 10 seconds. And statistics is a commonly overlooked feature of the clients, and it gives a lot of debug info and info that you can use in fault finding and just to see how your client's actually doing. So that's all the config that we require to spin up our producer, and that's actually the most difficult part of this producer. So we'll just go and create a producer now. We'll call it producer. We'll say that is a new producer builder. We need to specify over here the type, so we know that we want to pass in a key of type string as well as a value of type string, and then we'll go and pass in the configuration we just created as a parameter, And we can now say build. So this is that's in effect all we need to actually spin up a production grade producer. Now under the hood, this will handle all of the communication, all the failures that the networking, or well, that networks and so forth can throw at you. This normally even survives if your cluster goes down and comes back for a little while. But we don't want to end there. We do want to just be a bit more specific in this. So we do want to handle any errors that occur. And for that, we can set our error handler. And we'll just say handle errors or error. And we'll go and create that method. We can also say set log handler. Handle logs. And the last one, we just want to handle our statistics. So we'll say handle stats. So with that, we'll go and code up the statistics handler right now, but we've actually wired up everything we need, and we can now go and produce some messages. So to do that, we'll just create a for. We'll say we want 100 messages, and then we need to create our actual message that we want to send. To do this, we'll create a new variable, call it message object, and we will make that a new random anonymous function, and we want an int value in there that's equals to I. We also want a string value in there that is equals to I dot toString. Now this is the message you'll normally get in. Depending on your system, this is just a feeder message. We now need to go and create the actual Kafka message. So we will create message, and that's going to be of type message. So this is the Confluent Kafka message, and we need to specify a type for that as well. So this will be the same form as our producer, string string, and we can just new that up. Now with our message, we just actually need to do a new one. So with our message now created, we can specify some properties of this. And the first one is what Niels also alluded to, is the message.key. And this is used to say, where is this message going to? How am I going to partition this? Now we'll set this key to key dash to string, and then we'll go and also specify our message value. And for this, we want to actually use this object we've got, turn it into a JSON and serialize it into a string. So let's go and do that with JObject. From object, we will pass in our message object over here, and we'll call toString on it. The middle part might differ a bit depending on your application, how your message arrives and so forth. But we've now got everything required to actually produce this message. So we'll go and say producer.produce. And in there, we'll need to firstly specify the topic we want to produce to. We need to pass in our message. And then there's a delivery report. Now, delivery report you will receive whenever you get an error or if you get an actual success of your message sent. And we will do the function for that. And in here, what we can do is we want to handle, if there's no error, let's log this to the console. So we'll simply say if our delivery report dot error is error. So if it's not an error, let's just go and do a console write line. And this is once again one of the cool features of Kafka, because we are getting a delivery report, and this actually tells us something about the message we've produced. So what we know about this message is that we are getting back a partition. We're actually getting back a TPO or topic partition offset for this. We only want to print our partition, and then we'll like to print our offset. So here we can go dr delivery report dot partition, and also dr dot offset. So we all set, and we can now go and run our application almost. But if we were to run this, it'll exit immediately while it's still establishing a connection. So all we'll do, and this is good to throw into your live producers as well, is to say at the end, when you're exiting, do a producer.flush. This needs a time span, so we will say timespan.from seconds, and we'll say that we want that 10 seconds. Now this will ensure that our messages goes through, but I also want to show you the stats. So we'll just throw in an endless while loop over here. And we'll say that we'll do something silly like system.threading.sleep for a couple of milliseconds.
This is obviously production. This is obviously production code, eh?
Don't try this at home. So we're only going to handle the stats. And I'm going to do.
Can I interrupt you? Can I interrupt you for a second, Charl?
Perfect, of course.
So Andres have, and this is kind of a question related to what you're doing here. So Andres is asking, how does a producer authenticate with a broker? Can you set this in the producer config or in the producer builder?
Absolutely. So you actually set this in your producer config, and when we look at this, so that's a very good question, Andres. When we look at this, we don't have a very complex application over here to publish in messages, and it really doesn't get more complex than this. The only two reasons that it'll get more complex, well, three reasons maybe. If we do bad coding, that's number one. Secondly, if we're dealing with security, and in security, the biggest thing that'll change is actually your configuration settings over here. So if you do SSL, you'll need to specify your certificate that you're using over here, and also set your some of the security settings just in it's basically encryption that you'll use SSL. And if you're using something like SSL Scram, then you'll also need to pass in the username and password, so your credentials, and that might make your application slightly more complex, more to the fact that you need to keep those secure. So you'll probably need to use environment variables or something of the sort. I hope that answers, otherwise just send a follow-up question. But yeah, most of the security configuration and other settings are dealt with in the config itself. You don't really need to go and do anything much more to your producer. So with that, we are actually ready to run this thing, give it a bash. So we'll go into our control center. Now this is an enterprise component. You can use it free of charge for 30 days or on a single node cluster. And we just want to go and add a new topic in here called tests. This is the one we specified, and I'll give it two partitions just to show the partitioning. We'll create it with defaults, and I do love control center because I can go in here and I can say messages, and in a sec we'll see some messages flowing through. So we'll go and start our little producer, and hopefully everything works fine. So this is going to quickly establish a connection, and then we should see it saying hello world. No, I have done something wrong. Oh, it's just a warning. I stopped it very quickly. So it's going to say hello world. It's going to start sending off our messages, and we should start seeing our messages in the control center. And then indeed, we can see that we've got messages, and the nice thing is that we can actually see the structure of those messages. I'll zoom down just a little bit. So here you can see, even though we're just passing in JSON, we can already make sense of this. So we've got int val, string val. We can actually take a look at all of our messages in here. So we'll just stop over here for a second. And now this is the stats. I'm just going to zoom to somewhere where you can see it. So this is the stats I was talking about. And this really is a powerful utility to use to get some valuable insights into what your producer is doing, or even your consumer. And it's telling us latencies of the messages. It's telling us how many times this thing has failed, reconnected, and all kinds of cool stuff like that. So don't overlook this feature if you are starting to dev with Kafka. All right, so that's what I wanted to show from the producer. We'll quickly have a look at just the consumer. And what you'll see, hopefully immediately, is that it looks very much the same. All right, so if we go up here, maximize this, you'll see that we've got the same config, consumer config. This is a consumer config, it's not producer config, but it looks very much the same. We're specifying Bootstrap service. And then we specify an auto offset reset, and auto offset reset is telling us if you've not consumed from this group, do you start earliest, which will give us all the messages that's still in the retention period, or do I just consume from latest, which will give me all new messages? We also will specify the group. Now the group is saying of which group am I part of and serving. So this is for scalability purposes, obviously. But the cool thing is I can also specify a completely different group, which means I will operate separately and I won't influence the offsets of the other group. The last one to note here, or well, the second last one is isolation level, and this you'll utilize if you are dealing with transactions. So in Kafka, transactions are quite cool because you can set a transaction around different topics. So transactions are not for single partitions or topics, but you can actually, in a transactional fashion, send off different messages to topics, but then you want to set isolation level to recommit it. Last one is enable auto commit. We'll set that to false in most of our production applications because normally you do want to handle that at the finer grain to make sure that your message has actually been processed. So as an example, we will commit our consumer offset over here after every 10 messages that we've processed. So this was just a quick introduction to show you how easy it is to get started with a consumer and a producer. We're going to go back to Niels now, who will tell us about doing a bit more of our data in terms of ksql. Niels, I believe you are muted.
I'm definitely muted. I'm so happy that this is not a technical session. So how can we, so there was a question from Essen, how can we return offset partition when we produce instead of logging it, like as a return parameter for producer as a delivery confirmation? Maybe you can, I'll start sharing my screen here, and maybe you can either write the answer or do it fairly quickly verbally. I'm starting sharing here now.
So I'm just reading through that. How can we return offset partition when we produce instead of logging it? So you get back the partition and offset in your message. So basically you've got that in your code and you can deal with that at that logical point. So I don't know if that answers your question, but it's not actually logging it. I just logged it to the console, but you've got full control of what to do. So you can actually go and store that off into a different database if you've got such a requirement.
Cool, thanks, Charl. So Charl, that was very cool. We're now seeing how we can produce messages and we can see how we can consume messages. But so far, we haven't done really anything else than just a message queue system per se. Well, it's a distributed log and all that cool stuff that we spoke about before. But now what we want to do is we want to start handling these messages. We want to do stuff with the messages. We want to get insight into the messages. And that's when we now, and there is an app for that. And that app is CaseEqual DB. And once again, DB on the end is awesome. It's a database almost. So CaseEqual DB is an event streaming database. It originally was named ksql, so you will see in documentation, etc., they are mentioning ksql quite a lot, but that is now essentially CaseEqual DB with some extra bells and whistles on top of it. And what CaseEqual DB does is that it allows you to build stream processing application, real-time stream processing applications. And you do not need to write these applications using things like Java, Scala, or what have you. You can use this, you can use normal, kind of normal SQL. So it's an ANSI-like SQL. And if you need to do more things that is not supported by this SQL in CaseEqual DB, you still have the opportunity to write your own user-defined functions. In this case, you would most likely using Java or Scala and use them when needed. The CaseEqual DB thing lowers really the bar for implementing streaming. And before CaseEqual and CaseEqual DB, we had something in Kafka called case streams. And that was a fairly low level implementation where you worked with your records with your streams. But when I'm saying that we are lowering the bar for streaming, on the left-hand side here, We're seeing a CaseEqual DB statement. We're creating a stream called fraudulent payments, and we are saying that the fraudulent payment is when we are reading from a topic called payments, and where there is a field called fraud probability that is greater than 0.8. Right? So this is 1, 2, 3, 4 lines of code. If we were to write the same in case streams, it would be this, and I would need to know Java and God knows what else, right? So this is actually CaseEqual DB is really there to help you build streaming, real-time streaming processing applications. So when we're talking about CaseEqual DB, there are two concepts here that is extremely important. That is a stream and that is a table. And the stream is essentially the unbounded sequence of structured data. And we saw the stream when Charl was publishing into the topic. That is essentially a stream. And this stream is immutable. You cannot change it. It has happened. It's a history, essentially what has happened from day 0 up until right now. And it goes on and on and on and on. Whereas a table, you can create a table over the stream or another table for that matter. And then you can do things to the data, i.e. the table is mutable. So you can edit a record or whatever, you can ingest another record, etc., etc. And in the Kafka world, we're talking about the stream and table duality, and that essentially means that if I have a stream, I can turn that into a table using DML manipulations such as select, count, sum, various aggregates, etc. And we can also turn a table into a stream by capturing the inserts, updates, and deletes. And actually, in this case, turn a table into a stream, we can go down on a sort of on a real database level. So at Derivco, we have lots and lots and lots of SQL servers, and we are using something called CDC to capture inserts, updates, deletes into the table, and we are then publishing that as a stream. Very cool. So the syntax of CaseEqual DB. So the semantics is similar to ANSI SQL, as I said before. We have various statements we are creating. We can create a table, we can create a stream. Especially if we're creating a stream, we will combine it with select and insert, etc. And in create, we're supporting windowing functions such as session, hopping, tumbling. So we can say, okay, create a stream for every 5 seconds when something happens. We can do insert, we can do select, and a little bit more about that later, and more stuff. We have functions, we have support for functions, scalar functions, aggregations such as sum, etc., etc. And we have table values functions. So CaseEqual DB gives you, if you're used to normal SQL, syntax, CaseEqual DB gives you more or less the same. The last thing here before we will go back to and look at code is CaseEqual DB also introduced something called push and pull queries, where we are pushing or pulling against a table or a stream, and we are getting data back to an application. And a pull query is essentially what if you are selecting against a normal, like a SQL Server or MySQL or whatever database, you are selecting from wagers where this ID row key equals something, right? So that is now giving you back all the values where we have a row key of 1, 2, 3, 4, 5, and then it terminates. Then this query terminates. A push query produces essentially continuous stream of updates to another stream or a table, and we're saying select. So here we're doing a pass-through query, select star from wagers, emit changes. So as soon as something changes now in this stream, a new record comes in, this query pushes out the result to your application. And with that, hand over to Charl again to show some CaseEqual DB goodness. Charl, you are muted.
Okay, there we go. I was just finding my way. Thanks for that, Niels. So Niels has just introduced us to ksql DB, and this is really where Kafka and the utilities and tools on top of that starts to shine. Just going to move that out of the way. So it's not really about what Kafka can offer on its own, because we've had that, but it is about how easy it makes it to integrate and see value and get data or get value out of our data. And one of the main functions that enables it to do that properly is this replayability of data. But it's not only replayability, it's the fact that I can go back in time as long as my retention period actually specifies, so 7 days or 30 days or even longer. And I can go and just consume that stream of data, do my analysis, and if I mess up and do something wrong, I can simply go and do it again. And normally in an ETL world or a different world where you need to analyze this, you'll have someone that needs to go and get that data for you if it's available. So this is really one of the powers that Kafka and ksql DB gives us. So we are going to now do a couple of ksql queries, and then we're going to head on to some more advanced advanced basic and data analysis on that to show the integration. I'm going to start a Python producer over here to just simulate some data. This will simulate deposits and wages, and this is a Python producer. It's actually the Confluent Python supported or well maintained producer, and it looks pretty much the same. And this is also quite nice that even in the different languages, you start to learn to understand how you can, or what guarantees and so forth you can trust from Kafka. So we'll spin up this producer, and that's going to start producing some messages into our cluster, and we can actually go and verify that it's working over on our control center, and we'll see that it's created automatically a deposits and wages topic. This will also answer one of the questions that came through. So there is a setting in Kafka that you can set on the brokers, which specifies if you want topics to be created automatically or not. By default, it's on. We can go into our deposits over here, and we'll see that we actually have, if we wait long enough, we've got some deposits flowing in there. And once again, we can see the structure of those deposits. Very same is true for wages, and we can now go and start querying these wages in ksql DB. Now, normally to do some data analysis, there's always a story. So our story today is as follows. Our boss has said that if it's basically 20 years after the whole millennium debacle, and we need to get more insight out of our data. So he wants us to build this dashboard by Friday, and then we can have next week off. Now, this is going to give us a nice insight into our data, but this is really just aggregations, all right? But aggregations on real-time data is very powerful if you can actually trust them and get them in real time. So we're going to have total deposits, total wages, the summation of the amounts. We'll have average bid amount and average run amount, which will give us good indication of how our business is doing, and a min start and max end balance. And then we're going to have exactly the same metrics, but in a windowed fashion. So up top we'll have the lifespan totals, and down below we'll have a little window that gives us that for the current window we're in. So with that, let's set out to build this. We'll start off with creating a create table select statement. So we're going to create a table here to hold our aggregations, and we'll call that T stats. And actually, before we do this, we just need to quickly go and register our streams. So in here, we can go and register a stream. Now, a stream registration is basically saying we've got deposits as a topic, but we need to just register some meta information, making it available to query in ksql. So we'll do JSON encoding, and we'll set our username as the partitioning key. And that means we can aggregate and do joins based on that partitioning key. We'll save off that stream, and then we'll go and do exactly the same thing for wages. So also JSON encoding, you can use whatever encoding you're actually sending your messages into there, and you can also change it, and we'll do that on the same username key. So now we've got our two streams. You can go back to editing our query. So we'll select our type field over here. We'll then select account all as count deposits, and we'll do a sum of deposit amount, sum deposit amount. And we're going to be doing that from our deposit stream, and you'll see there's some IntelliSense there. It's getting better with every version. And then what we'll want to do is we're going to group this by type. And because this is CaseEqual DB, we've got the notion of pull and push queries, as Niels alluded to, and this is going to be a push query, so we need to do emit changes. What we also want to do is we want to go and add our auto offset reset here to earliest, which means we've got data coming in, but we actually want to analyze all of the data and aggregate all of the data since the beginning of our publisher. So we'll just set that to earliest. And with that, we'll give it a once over. It looks fine, and we can now go and run that. It's going to come back at the bottom saying, good, we've posted your query over the REST interface. It's all there. And we can actually go and confirm this in the new version 5.5 of Control Center in this flow layout. And this is saying that we are creating a stream from deposits. We can have a quick peek at its creation statement. And indeed, we can see that we've got deposits coming in at a steady rate. Now, the second thing we wanted to do is we wanted to do the window over this. So we'll just go and change this to window 10s, a window of 10 seconds. And then we'll go underneath our from deposits and say window tumbling, and we need to specify a size. What we're doing here is we're saying do this aggregation, but do it every 10 seconds. And the tumbling window tells us it's a gapless window that follows on each other, so it's non-overlapping. So we'll go and run that. And we'll get the success for that. Then I'm going to do 2 more for the wages. They are a little more lengthier, so to save time, I'm just going to paste them in here. And over here, this is our wages. We'll do the same thing, but we're going to be doing aggregations, sum, average, min, max across our bet and win amounts, and then also a min and a max on our start and end balances. We'll make sure that we're still on earliest, and then we'll give that a run. Well, that's happy, and then we can just do 1 more, and this is exactly the same query, but just with a window tumbling of size 10 again. Okay, so we'll go and see that all of our 4 new tables are there, and with that we can actually go and run our little application. Now, this is a normal .NET application. It's the normal consumer that we actually just did in the previous one as well, so the Confluent one. We'll hit start, that'll spin up if we've not made any mistakes, and it'll start consuming all of those messages. Now, what's rather cool is these messages are flowing in real time, so these are events that you're actually seeing updated. It's not a query going anywhere, this is just the events that we're analyzing, grabbing the value from the JSON object and populating the label. Now, what is rather cool about this is that you can go and push this into a stream and turn your front end into an auditable view of the data that you're seeing here. And that's something that is becoming more pertinent in the times we live in, where we need more data governance and we need to be auditable in what we do. So if we look at this, we can see that we're actually making a bit of money. We've got an average bet amount of 404. It's interesting. We've got a win amount of 385, so definitely a bit of money coming in. And then the window at the bottom here, you can see kind of at the current time slot what we're doing. Now, if you do these windows over a 7-day period or the period that suits your business, this could give you some very cool insights into how you're performing right now against your lifetime totals. The interesting thing to note here, however, is that we've got a minimum start balance of negative. Now, yes, I planted that little seed, it's me, but this could be a real case scenario, and we know we need to go and analyze that. So let's go and do that. So that's our UI. We've done it before Friday, so we'll chat to our fearless leaders. But now we want to take this further. So we know that we've got bits coming in with negative start balances. Now we can go and push that into a stream in ksql very easily. So what we'll do is we'll create a stream as select. Notice that we're not doing another table here. We want to actually flow through all of the events as they come in, but we want to flow them into another stream that we can go and analyze. So we'll create the stream, we'll call it S suspect wages. And we'll simply select anything or everything from our wages table where the bet amount, where the start balance amount less than equal to 0. And we need to remember to emit our changes. This will go and create a new stream S suspect wages for us with all the values where our start balance amount is less than or equals to 0. So let's go and do that. That's been created successfully. In our flow, we can also confirm that we now have S suspect wages and we've got data going in there. Now at this point, what I'm going to do is I'm actually going to kill my producer over here. So it's midnight, guys, I've stopped playing. And what I want to do this is I want to show you that with our next set of analysis, we're actually going to use this replayability or this fact that we can go back in time to do analysis on what has happened already. So we've stopped our producer. And now we're going to jump in and see how we can integrate further with other tools using the power of Kafka to do some more analysis on this. So I've got a Python notebook open over here. Just going to expand this. And this is basically in the Visual Studio Code, just using the extension. And notebooks are really a cool way just to analyze your data and store the output.
Charl, you disappeared there.
We apologize. We just seem to have lost connection with Charl. We'll try and reconnect shortly. You could just bear with us as we connect.
So what Charl is going to show us here is how we are using what we call Jupyter notebooks to interact via Python with Kafka and do almost machine learning things against the data that we are reading off Kafka. I think we have Charl back.
Apologies, it seems I disappeared there for a second. So cool. So Niels, just quickly, what was the last that you guys saw?
That you essentially brought up the notebook. And that was the last thing we saw. And I said that you were going to do cool stuff with Jupyter notebooks in VS Code. Perfect.
So we're bringing in a couple of libraries over here. We're bringing in pandas, which is really cool to work with data frames. We'll bring in matplotlib, which is going to be used for plotting our data. And we're bringing in Confluent Kafka, and this is really just to consume the data that we have been generating. So we'll just import all of them and we can get cracking. So this is a normal consumer, Python consumer, using the same base. We'll generate a suspect wages list and we'll go and subscribe to our suspect topic, which we just created, and we'll just add that to our list. So that's going to run, and that's going back and getting all of our messages from Kafka from the suspect wages topic. And as soon as that's executed, we will take a quick look at it and make sure that we can work with data. So we'll look at the first one, and indeed we can see there's our bet amount, in balance amount, and our start balance amount. So now we're going to actually use pandas and create our first data frame, passing in our list of data, and we'll call it df suspect. Now, what data frames gives us it gives us the ability to just do df suspect. So just call it, and that'll give us a quick summary of our data, what it looks like, the first 5 rows and the last 5 rows. And we can scroll through that, but it really doesn't tell us much about our data. Additionally, we can go and call dfsuspect.describe, and this is going to summate or give a summary of all our data and our columns. And what we can see here is that we can see indeed we've got negative start balances all across, a couple of guys doing this, but we also have guys winning. So players winning with this negative start balance, and we don't necessarily want that happening. What we could also pick up is that the bet amounts seem to be the same for all of the different percentiles. Now this is interesting. So we'll go and look at that in a second. If we look at our suspect info, this gives us meta information about our data frame, and we can see that we've got 827 entries, and that's taking up the whole of 51.8 kilobytes. And the reason I'm showing this is that it needs not always be very difficult to analyze your data, and you can do this in subsections with your data utilizing something like Kafka. So it is an enabler to actually go and understand what's happening in your data. Now we can do a suspect.plot, and this is using matplotlib, and this will show us quite an interesting view of our data. I'll open this in a bit different view here. So we can see that, yes, there's a lot of negatives going on here, but an interesting thing is these orange lines that go to the top, and the orange lines is our end balances. And this means that we've got end balances that's actually going into the positive, and we want to analyze that because it means we're only seeing a part of the picture. So we'll do a suspect plot histogram on end balance amount, and that'll confirm that we've actually got guys ending on the positive over here. So let's focus on them and see what that looks like. We'll do a new data frame called dfposEnd by specifying we want everything that got an end balance amount greater than 0 from dfsuspect. And we can then go and plot that as well. And here we can see, indeed, there's a lot of guys that's actually going into the positive here. So we've excluded them in our initial analysis because we are starting to analyze the problem, but we can now go and dive deeper and try and understand the behavior that we are seeing here. Furthermore, we can just scatter it and see if there's any patterns that we can look out for. And this is just telling us that it's pretty sparse. So in this case, nothing new. Let's go and go ahead and just see this amount. So we've got a bet amount of 3.14.159, and we want to go and get more information about bets that's got that specific value. So we'll head back to CaseEqual, and we'll create a new query, or stream rather, saying suspect wages bet amount, and we'll say that this we want where we've got a bet amount equals to amount we've seen. Make sure it's earliest, we'll run it. Remember that we don't have any data being published into our topic anymore. Our producer is gone, but still we are able to actually go back and grab all of this data and do this analysis on it now. So with that created, we'll head back to our notebook, and we'll go and consume our suspect wages bet amount. So we're just creating a new list over here. That'll go and consume. We're also specifying just the new suspect wages bet amount group ID. We can control that and setting from earliest. So that's consumed all of the records. Now we can go and see what it looks like. So with our bet amount, we now have hopefully a greater view of the impact of this specific wagering pattern. So we'll create a new data frame from it. We'll go and describe it, and we'll see that for all of these bets where it's 3.14159, we are actually seeing a whole bunch of start balances in the negative, but also quite a lot in the positive. We can go and confirm that by plotting it. And this actually gives us the fuller picture of the impact of this behavior. So we can now see that guys wagering with this amount are making quite a lot of money here. We can also do 2 more scatter plots. So the first one will show us that it's a pretty random distribution of wins in terms of the big wins, so we can't really pick up any pattern here. But if we do a scatter plot on the start balance and end balance amount, this will confirm that we've got in the top right section guys that's starting with a pretty high balance, wagering the same amount, and obviously walking away with quite a bit of money. So this is quite cool. Now to end off with, we're gonna, so right now, just to quickly recap, we've done filtering, we've done aggregations, and we've done this all in a language, SQL-like language, very much closely related to ANSI SQL, where we've got now valuable information out of our data. But now we can go further and we can actually create a dynamic table on this that builds itself by interpreting this wages stream. So we'll head back to our editor and we'll go and create a table on the suspect wages bid amount. So we know that these are the wages that we're interested in, and we can go and create a table from this. So we'll head into our tables, we'll say add new, we'll pick suspect wages bid amount. This is JSON encoded. We'll do this on username, and over here we actually just want to build a table with the username. So we'll call this T suspect users. And we don't need all of these fields. We actually just want the username in this table. We'll go and save it off. And now we're going to write a query that will join this table we've just created with our wages stream. So let's walk through this quickly. So we are saying that we're creating a stream as suspect big wins. So we want to know if suspect users have big wins so that we can kind of go and look at them immediately. We'll select the username, the win amount, start balance, and end balance amount from wages, and then we'll left join on our T suspect users. So this is that table that's automatically going to update itself with the stream coming in. And that we're going to do on row key equals username. So the wager row key equals the user table username. We'll specify a where in here to say where our user has an actual value. There's different ways to do this, but we want the ones that we actually have a valid join on, and where the win amount is greater than 1,000. We'll go and run that, and in our flow, we can see that we now have our suspect users table joining to our wages and giving us the suspect big wins, and we can actually go and confirm and see that in total, up to now, we've had 169 of these big wins. We'll quickly jump back to our notebook, and we can go and consume these. So once again, we're consuming our S suspect big wins that we just created, specified a new group ID over here. And that's now consumed. So we'll look at the first entry, and there we can see all of the fields that we've selected. We will create a data frame from this, and then we will go and describe this. And now we can see the impact of all of the big wins. So we can see that 75th percentile of big wins amount to 4,450, and you can get a very quick breakdown of the impact this is actually having. And lastly, to end off with, we will go and plot that. And this is a real-time representation of all of the wins, all the big wins since we started up to now. That's giving us a quite interesting view of how our business is doing. So this was quickly to show just how we can get started with CaseEqual. And I mean, CaseEqual once again is a DSL on top of something more powerful case streams, but it depends on your use case where you want to do this. However, Kafka does allow the underlying broker and the underlying feature set that we require to go and work with our data. And then we ended off just to quickly show how we can integrate something like Python into actually harnessing that powerful features to get some insights. That's all from me. Niels, I'll hand back to you to summarize all of this for us. Thanks.
Thank you, Charl. I think I'm unmuted. I hope I'm unmuted. I'm sharing my screen here, and we should see a summary coming up soonish, and I'll move this little window over there. So thank you, Charl. Awesome. We have seen CaseEqual DB. We have seen how we are interacting with Python and pandas and all that cool machine learning, data science stuff. And we can take this a lot further. So to sum it up, we started, actually, I started talking about data, how important it is that we can look at our data to get insights in our data. And the session today, I hope it has given you a feel for how easy it is, together with Kafka and CaseEqual DB, to do stuff with your data. We spoke about the distributed streaming platform that Kafka was, sending messages point A to point B, persisting messages, etc., etc. We spoke about topics partitions, offsets, and consumer groups, and then finally we actually saw how CaseEqual DB lowers the barrier for entry to write real-time streaming processing applications. And that is that from us. So once again, thank you guys for taking your time and attending this webinar. There will be more webinars coming from Derivco, I hope. And now questions. I do know that we have quite a few unanswered questions in the Q&A session. So Charl, shall we start having a look here?
100%. So I'll just start trolling through them from the top. Andres made a comment, Kafka is basically a distributed transaction log, 100% correct. So you've got the notion of a transaction log, but that is distributed. So when you drill down to a partition level, then you've got that set or that partition being all secured into a commit, to a transaction commit log. I mean, we can go down further there. The actual storage function, there is a segment, but I think that's that you get to when you really start diving into the details. But yeah, a partition is a distributed commit log. We will go down. So Wesley's question we've answered. Are there size limits for partitions? Niels answered the, I think, a portion of the question. So yes, there are limitations as to the amount of partitions you can currently run. So this does depend on the size of your, well, the setup of your brokers and so forth. But there's a big limitation at this point in time, really, on the Zookeeper impact. So right now, it's proposed to have in the order of 4,000 partitions per broker. But obviously that's just a proposal. It depends on other factors, but that will be removed when we see the removal of the Zookeeper and KIP 500. Scott asked advantages of using Avro over the other messaging formats. So Scott, I think Niels kind of gave a very good answer there. So previously there was some good advantages because it was integrated with schema registry and JSON was not yet. But as of the last version 5.5, JSON is fully supported together with protocol buffers in Kafka. So when you look at most production instances, it almost seems like JSON is going to be the flavor of the week, because a lot of guys are used to JSON. There's also quite a big spectrum of users that's into protocol buffers. So I think the answer here is it depends on what you're doing already and what you know in your organization. But the support certainly has been ramped up for all of the protocols.
So Charl, Wesley has a quite interesting question here. So how does the consumer know which partition to look at for a given topic?
How does the consumer know which partition to look for? Okay, so maybe let's quickly stand still for a second on that one. So when you start consuming, the first consumer, what it will do is it'll communicate with the broker, and controller will be selected. So one of the brokers is going to be the controller, and that broker will, in essence, maintain or look after the group membership. So if you've got only a single client, what it'll do is it'll actually assign all of the partitions to that client. So because it knows that that's the only client currently alive. Now what's going to happen as soon as you spin up another consumer in that group, so specifying the same group ID, that client will basically communicate to the controller. It'll say, I'm here, I'm alive, I want to get some partitions. and then there will happen a rebalance. So basically an election will happen and the partitions will be rebalanced. And this is on a couple of factors, but in essence, you should see a pretty even balance being given to your different consumers. And there's quite a lot to that protocol in terms of how those are assigned. But what's important to note is that once again, you can only have as many consumers as you've got partitions. So as an example, if we've got 4 partitions and we spin up 5 consumers, 4 of them will be active. They will each be assigned partition because I can only have a single consumer per partition. And the main reason for that is order, because as soon as I add another distributed consumer, I tend to lose my order. And then what will happen is if one of my other consumers die, the 5th consumer will actually enter and be assigned a set of the partitions as well.
There are questions around size limits. So we had a question here, was the max size allowed for a single published event? And I kind of returned back with a default 1 meg for a single event. Kafka is essentially optimized for smaller messages, but yeah, up to 1 meg at least.
Yeah, so that's a setting that you can also go and set, so you can tweak that a bit. However, it's not best practice to really go over a meg in any kind of streaming messaging system, but I mean, you can go and set that. If you are, however, hitting messages of a meg, you probably set a very interesting use case, and I think one could go and look at what, are you using the correct technology for that? I mean, a meg event is pretty big, so that's like sending real-time images every second. Once again, Kafka can handle bigger messages. However, if you go over the meg limit, you need to set a couple of settings in relation to that.
So there's an interesting question here by Esan who asks, what's the pros and cons of ksql DB over Apache Spark? And yeah, that's a really, really good question. And this is now the typical database developer answer. It depends. So it depends what you want to use it for. So first of all, ksql DB more or less comes out of the box with Kafka, so you have it. Apache Spark, well, you may have it in your environment, and yes, obviously you can use Apache Spark for this. And so it comes down to what do you want to use it for? So if you're going to use it for mostly just simple filtering queries, creating streams, creating tables, then ksql DB is the way to go. If you want to use it more for real-time Spark streaming with machine learning, well, then Spark is your answer. So once again, it depends is my answer. Sorry for not being able to give a better answer.
I think maybe just to add to that, Niels, so this really is one of those things where Kafka is dealing as the broker, and I think that you need to view as almost a separate, but Kafka integrates very easily into stuff like Flink, like Spark, and there's definitely deployments out there that would utilize a Spark with Apache Kafka, linked to it. There's actually quite a big cool blog post that'll add in just now related to this. So there's the world of complex event processing, really, and then there's this event of stream processing. And in the event of stream processing, when you look at Flink and Spark and ksql, a lot of them tend to be growing in the same fashion, starting to support the same functionalities. There's little differences. As an example, Spark used to be micro batching in how it works, where when you work with something like ksql, that's tied a little tighter to how Kafka operates. But I think, once again, a good answer from Niels is that you need to go and look at what you want to do specifically, because some of these frameworks might be more suited. If you're a Java shop, it might be more suited to use something like Flink, Spark, or even then K-streams. But when you a DB shop, you want to do as much as possible, obviously in something like ksql, or even then when you're going to Spark, something like Spark SQL.
Cool.
There's a question from Eric. Does CaseEqual DB support Kafka's exactly once processing semantics? And the answer is yes. So when you look at the whole Kafka landscape, everything in the Kafka ecosystem is working on the same guarantees that basically Kafka gives, because everything is a producer-consumer. And when you look at CaseEqual, that's got the support of RocksDB underneath it, and you can extend on that when using case streams to use a different store. But in effect, that is giving you those exactly once processing semantics, because it's got a state that's distributed, but it also has the exact offset of where you're at and where that processing is at. And this is quite a big leap that's come in the last couple of years when we look at CEP, or complex event processing, because the world of complex event processing tends to live in memory, and it tends to, in the little bit older day, actually chuck away messages, when something goes wrong. A lot of the CEP frameworks out there has actually started utilizing things like Kafka in their backbone to overcome this problem.
Anonymous has a question here. Use cases of Kafka. Yes, yeah, that's whatever you can think of. So at Derivco, we are using it for actually we're using it for two main things. We're using it for real-time stream processing, as we have spoke about here with CaseEqual DB and stuff. But we are also using it for just stream the events real time to various consumers inside and outside of Derivco. Then you have the likes of New York Times, who is storing everything they have in Kafka. So all their articles, all that stuff is stored in Kafka, and that's quite an interesting use case. At Derivco, we are definitely not there yet, but maybe someday. So yeah, it's a too broad question to really answer. But obviously, event streaming is one thing. Use it as a message bus if you want to, but utilize what it's good for.
Cool. Thanks, guys. I think that will bring everything to an end. Thanks for joining us today. That's the end of today's session. If you'd like to join us for future events, keep an eye on our socials on Facebook, Twitter, Instagram, and as well as LinkedIn. We also want to make sure that these sessions are the best ever, so who better to ask but you? So look out for a short questionnaire that will be sent out tomorrow. Please share what you liked, what you didn't, and suggestions for future topics. Also, if you would like to rewatch the session, we'll be uploading it to our YouTube page by tomorrow. I think that's all from me. Thank you once again. Stay home if you can, stay safe, and see you soon.